Thank you all for coming out today. My name is Nuno Subtil. I'm a dev tech engineer at NVidia, where I mostly focus on helping game developers with the Vulkan API, and particularly with ray tracing. And so I'm here today to talk to you about ongoing efforts within Khronos to standardize a ray tracing extension. So we're going to try to cover briefly how we're planning to bring ray tracing to the Vulkan API in a cross-vendor way. Some of you may be aware there's an NVIDIA extension out there for ray tracing. We'll go over the details of how the cross-vendor version will work instead, with some caveats that I'll explain later. So the outline for my talk is essentially this, heavy on the motivation for ray tracing and why we think ray tracing is important for the future. And an overview of the current ray tracing ecosystem, particularly focusing on Vulkan applications out there that are making use of ray tracing right now. And then we're going to go into what I call a bit of a shallow dive into the API itself. So let's get started. So I guess I'm standing in front of what I bet are a bunch of game developers. And a lot of you are very experienced with rasterization-based techniques. Which is what GPUs have evolved to do today. They're massively powerful rasterization machines. And to compare and contrast what you can do with rasterization versus ray tracing, let's go over some of the details about how those two differ. So with rasterization, your input data will be, in your 3D world, you have a set of meshes which end up being represented as lists of triangles. Triangles have positions, so 3 points in 3D space, plus some number of other attributes along with those vertices. And with rasterization, what you're doing is traversing that list, and for each triangle individually, you're going to process it, you're going to run your vertex shader, project those vertices onto the screen, and then the rasterization bit is where you figure out which pixels on the screen are actually covered by your triangle. And for each of those pixels, you're going to run some sort of pixel or fragment shader to determine the color of that pixel. So effectively, the rasterization will compute a number of things for you. It will interpolate position and attributes within your triangle inside the area that is covered on the screen. Your fragment shader has access to those bits of data, but crucially, it does not have access to anything outside the realm of this triangle, right? So any input data you need to do your shading needs to be attached either directly or indirectly to each of the triangles that you're processing through the rasterizer, right? A concrete example of where this becomes kind of difficult is if you think about implementing shadows, for instance. And shadows are ubiquitous. Every scene has light sources, so every scene has shadows of some sort. But how do you actually do shadows in a rasterizer? Well, if you're processing one triangle at a time, you don't actually know if there's any other primitives in between this triangle and the light source. So you can push in data on where the light sources are in your scene, but you cannot actually have access to data on what other primitives may or may not be in the path of the light for each pixel, right? So obviously we've come up with many clever techniques like shadow maps where you overcome this by generating a separate image which represents distance to the light from the point of view of the light itself, which means you're processing geometry all over again for each of the lights. And you're generating a texture at some resolution, but the sampling rate is not necessarily going to match what you need for your forward pass, where you're actually computing pixels on the screen itself. So you end up with aliasing problems on sampling the shadow maps and memory consumption for these textures. So you end up with even more creative solutions for some of these problems, like shadow map cascades and so on. So it just gets more and more complex. And again, shadows are ubiquitous. Every scene has shadows. But it turns out that most of these effects are really, really hard to render with rasterization. So rasterization is not popular because it's easy to use. It's popular because it's computationally cheap and very, very, very amenable to hardware implementations, which is why most GPUs today are massively powerful rasterization machines. In contrast, with ray tracing, you're not traversing a list of triangles and evaluating them one at a time. With ray tracing, you're defining rays in your scene with the starting point in a direction, and you're shooting rays into the scene. You're intersecting each ray with the entire scene. So you're evaluating the whole scene one ray at a time, right? there's no limit on what kind of rays you can shoot or how many rays you can shoot, other than obviously time budget. There's no limit on how many times you can visit a given primitive. There's no limit on which primitives get visited first, which primitives get visited last. There's very little constraints on sampling the scene. This makes for an extremely flexible approach to image synthesis. So with ray tracing, you can actually go all the way to simulating how light propagates within a scene, right? So, light emanates from light sources, it bounces around objects in the scene, it eventually hits the observer, having been modified by material interactions with all of these surfaces in the scene. You can actually simulate all of these paths and integrate over time to reach an image that is physically accurate. In fact, you can go as far as, instead of just computing some set of RGB values that will be somehow interpreted in some way by your display to generate a color that looks kind of like what you intended, you can actually compute physical quantities. You can define an array as carrying a spectrum of light and sample along the spectrum. You can do all of your rendering with physical quantities such that you actually get a physical quantity back if you choose to do so. Obviously, that may be overkill for many applications, but just to illustrate the point that ray tracing is extremely flexible and it allows you to simulate down to the physical principles of how light propagates in a scene if you wish. Of course, the caveat is ray tracing can be computationally intensive, but we have now reached a point where current gen hardware is now capable of doing ray tracing in real time for certain effects, certain applications in real time. And I have a few examples of some of the applications we've studied at NVidia for real-time ray tracing. I talked a lot about shadows. This is a good example to start with. So this is a scene where there's a window in the back, which you cannot see, and the sun is shining through the window, and there's a bunch of objects in a kind of a living room style setting. And so we're just computing shadows for a single directional light here. But you'll notice that all the shadows in the top, I'm talking about the top image for now, all the shadows are pixel perfect. There's no aliasing artifacts due to sampling rate mismatches or anything like that. There's no shadow map cascade transitions being blended between, nothing like that. It's just accurate and pixel perfect. And all you really need to do is trace one ray per pixel towards the direction of the light. And you can actually get by with less than that. But conceptually, tracing one visibility ray is trivial with a ray tracing approach. But with ray tracing, you can actually go farther than just pixel perfect hard shadows. So if in the bottom image we're trying to show that if you put a translucent curtain over the window, you're now essentially modeling an area light, right? So sun hits the curtain, it scatters, and light gets scattered in multiple directions by the curtain. So you get this kind of soft shadow where the curtain is now an area light, effectively. And area lights are also really difficult to render with a rasterizer-based approach. But with a ray tracer, it's relatively simple. Instead of sampling one direction, you pick a bunch of random points on the light and you sample those in average, for instance. You might do something a little more complex, but conceptually, it's still trivial to add this sort of functionality in a ray tracing approach. So what you get is this sort of contact hardening effect where shadows become more defined as you get closer to the occluder object itself, and they get softer as you start to move away because more of the area light is projected onto those areas than close to the object. Ambient occlusion is also a really good application. So ambient occlusion is essentially a lighting term that tells you roughly how much of the light that's randomly scattered throughout the scene is hitting a given point, which you can try to approximate by figuring out, for a given point, how many objects are in close proximity to this point. The more objects, the less light you're likely to receive from this ambient term. So typical rasterizer-based approaches use screen space algorithms that rely on the depth buffer. So you accumulate a depth buffer in your forward pass, and then what you do is you kind of ray march within the depth buffer for each pixel that you're evaluating for AO. You kind of do a little bit of ray marching around that based on just the information you have available in the depth buffer, which of course limits you in terms of accuracy. So in a perspective projection, as you get further away from the camera, you're going to have less data to work with, right? One pixel delta in a point that's further away from the camera is going to give you a much bigger distance in world space than a pixel delta closer to the camera. So you're limited in the amount of information you can capture or you can sample using these screen space approaches. With ray tracing, you can actually sample the geometry itself. So it doesn't matter how far away you are, you can still sample it just as accurately, right? And so this is evident, well, if you're using ray tracing instead of ray marching along the neighborhood, you just shoot rays that are bounded by a small distance from the origin around each point that you're sampling in, let's say, random directions, and you count the number of rays that hit something else. And if you do this with ray tracing, you're sampling the geometry directly, so you're not suffering from these aliasing artifacts or sampling rate issues that you run into with screen space algorithms. So, you know, you'll notice that the basket itself has a lot more detail, a lot more contrast, and so do the pillows and like all the creases on the sheet on the couch and so on. And when you composite this back on, this is one of my favorite algorithms to show off. When you composite it back onto the final scene, it brings out a lot more depth than you can get with a screen space algorithm. And you can't talk about ray tracing without shiny reflections. This is one of those things that is also trivial to do with ray tracing. So if you hit a shiny reflective object, you can very easily compute a reflected direction based on the normal, and you can just shoot a ray in that direction, and whatever it hits, you compute color going down that path, and you blend it with the material itself, or you know, do whatever your shading model requires to incorporate that reflection into the material itself. Anyone who's built a simple Whitted style ray tracer has probably done glass spheres and ray traced that. And, you know, you get reflections trivially by expanding the algorithm just slightly. With typically with rasterization-based approaches, you're limited to a mix of ray marching and screen space for screen space reflections, meaning that you can actually just reflect accurately any dynamic objects that also show up on the screen. Or you might have static environment probes that contain a subset of the data in your scene and that artists will place manually along the scene to try to get reasonable data for your reflection paths. With ray tracing, all of that goes away. You can just shoot a ray and get color, and you can get information from stuff that's behind you that's just as accurate as stuff that is in front of you. And you can go even further than this. NVidia has shown a version of Quake 2 that is fully path traced. It runs in real time, 60 frames per second at 1080p and current hardware. And instead of rasterizing, what it does is it shoots rays into the scene and follows those rays as they bounce around randomly through the scene, gathering light from those light propagation paths that will reach the viewer later. And you can synthesize images that look pretty good and realistic this way in real time. And you get all sorts of bonuses with that, like, you know, if you notice the light shafts in the sun, that's all dynamic. You can adjust the light to the time of day in real time and everything responds accurately. We don't have artists, or, well, we do have artists at NVIDIA, but not as many as you'd find at a game studio. So for us, it paid off tremendously to be able to simulate instead of baking stuff in. So all of the stuff you see in these images is simulated in real time for Quake 2. So a quick overview of the current ray tracing ecosystem. I mentioned there's the NVIDIA extension for Vulkan that's shipping. Currently, only NVIDIA implements it. There's also Microsoft's DXR, which is their extension or API for the ray tracing on DirectX 12, which is cross-vendor. As far as ray tracing capable platforms, NVIDIA recently launched the Turing GPU architecture, which supports ray tracing acceleration in hardware. And we also have support for the ray tracing APIs on older generation hardware, like Pascal and Volta, through a software implementation for both Vulkan and DXR. Without going into a lot of detail, but I'm sure everyone knows what I'm talking about here, there's been recent market announcements that suggest that other mass market platforms are probably going to get ray tracing capabilities in the near future. So ray tracing is expanding in the market. And ray tracing capable applications have been showing up. I have a very much non-exhaustive list of apps that have shipped or are about to ship with ray tracing support. So going into some more detail, I have a few images. They're a little dark on the screen, but hopefully you can make out what's going on there. This is a screenshot from Wolfenstein Youngblood from Machine Games. The game has launched over the summer, if I'm not mistaken. And NVidia has announced that we're partnering with Machine Games to bring ray tracing support to the game. So this is what the game looks like. If you download it and play it today, you go to this area in the map, you'll see something roughly like this. With ray tracing, we're starting to bring out some more detail into the scene. So in particular in this shot, we're showing off reflections from the puddles on the ground in front of the player, where you can actually see objects that are not visible on the screen but are reflected in the puddles correctly. This is done in real time, and it really adds to the immersion that you get from playing the game. If you have characters moving around, they will also reflect correctly on these puddles. You know, any action that's going on, particle effects, all of that stuff reflects correctly. And it really adds to the immersion, to the sense that stuff is believable in the game compared to typical approaches which just incorporate rasterization and don't get all of this dynamic info for the reflection data itself. Another application that's making use of Vulkan ray tracing is the Chinese MMO JX3 Online. So this is seen from the base rasterizer pass where there's a boat on the water. And one of the effects that they implemented, which I think worked out pretty well, is simulated water caustics. So by simulating the path that the light takes as it traverses the water interface, you can get caustics to come up in your scene, which again I think really adds to the depth and believability of the scene. And we have a few more images from Quake 2. So in this case, you can see there's God rays, so we can simulate participating media. All of this is dynamic, so you can move the sun, the God rays move just as you would expect. You see that there's indirect lighting towards the ceiling, and I'm afraid the colors don't show up very well on the screen, but you can see that there's a bit of a color shifting as you move up in the ceiling. You can also do accurate transmission in water, so you can get God rays that bend accurately based on the refractive index of the water. You can get shadows that are refracted correctly. You can also get, if you look up there, there's refraction going on at the water interface, so you can see stuff that's above the water and it's refracted correctly. And finally, if you have shiny light sources, which would be really tricky to model otherwise, you can see both reflections of things in that LCD panel-ish on the wall. You can see reflections of things that are not visible in the scene, they're pixel perfect. You can also see like the light sources on the panel are affecting materials nearby. So on that far corner, you can see that there's some green light bleeding over to the material of the wall, along with red light up top. All of this is simulated in real time, so none of this is baked, none of this requires artist intervention, it just works. So, having hopefully covered the motivation bit, let's take a tour of what the API for ray tracing in Vulkan might look like. But first, let's talk about the caveats. So as I mentioned, the cross-vendor extension is under development. And Kronos is typically fairly cagey about releasing details of stuff that's in development, for good reason. So we can't share too much detail on that just yet. However, we can say that the current version of the extension that is in development is largely based on and functionally similar to the NVidia vendor extension. So we're going to use NVIDIA ray tracing as a proxy for what the cross-vendor API is going to look like without revealing specific details on the cross-vendor API itself. Now, keep in mind, the cross-vendor API hasn't shipped yet, so things could change, although the fact that we're here talking about this means we're fairly confident that there's a low likelihood of that happening, but you know, things could change along the way, so keep that in mind. So we'll be presenting concepts from the NVIDIA ray tracing extension, not a cross-vendor version. We expect a cross-vendor version that ultimately comes out to be a superset of what we're talking about here. And the functionality we're presenting should be very similar. So in my mind, you can actually use the NVIDIA vendor extension for prototyping if you would like, and it should convert fairly easily to the cross-vendor extension later on. But keep in mind, this hasn't shipped yet, so things could change. I have to make that caveat very clear. So let's first do a quick overview of the graphics pipelines for raster and ray tracing. So for rasterization, I'm not going to spend too much time on this, but this is the basic pipeline. Draw calls go into some fixed function scheduling block that launches vertex shaders. This feeds as a rasterizer with work, and there's some expansion going on since 3 vertices generate potentially many pixels. Rasterization is typically fixed function block in hardware. It can also be thought of as sort of a scheduling block that schedules work for the fragment shader. Fragment shaders run in multiple threads, 1 per pixel. They generate work for some raster output stage that then writes that out to memory, and that's how you get your image, right? For ray tracing, the pipeline looks significantly different. So we start with a programmable stage that does ray generation. This is essentially a shader that generates the rays that are going to be the initial rays that are shot into the scene. This goes into some fixed function scheduling block that takes a bunch of rays, maybe reorders them for coherency or whatever the implementation may require, and generates work for a semi-programmable stage that does traversal of the scene along with intersection of your rays with the scene primitives. This is semi-programmable in that the intersection can be a custom program for custom primitives. Traversal, by and large, we expect to be a fixed function, or at least opaque to the developer. So this generates lists of intersections that go into some other fixed function block that does scheduling for these intersections to be processed by hit shaders. So we're going to introduce this set of new shader stages, one of which is the hit shader that takes as input an intersection, whatever that data may be, and computes shading properties for that intersection. Now, crucially, from a hit shader, you're going to be able to trace more rays, right? So if we're talking about reflections or shadows, that implies that at the point that you're shading, you may want to trace a ray, right? So this pipeline has the ability to generate more data from the back end that feeds back into the first scheduling block, hence the arrows pointing back at near the beginning of the pipeline. So in terms of building blocks, we're going to define 4 new building blocks on the Vulkan API. One is an acceleration structure. That's an abstraction for scene geometry that we'll cover in a bit. We're going to define new shader domains for ray generation, hit shading, and so on. There's going to be this new concept of what we call a shader binding table. This is a table that links different shaders with different resources used by those shaders. And we'll go into a bit more detail on this as well. And also, we're going to define a ray tracing PSO, which is analogous to a rasterization PSO. It's a collection of ray tracing shader binaries. And it's actually relatively simple compared to the raster PSO in practice. So I talked about acceleration structures. And I also mentioned earlier that when you're doing ray tracing, you're evaluating the entire scene. So each ray will be intersected against all the scene primitives. Now you can do this with a for loop that loops over all the triangles. I may or may not have built a ray tracer like this in college, but it is prohibitively expensive. You don't want to do that. And there are acceleration structures, there are data structures, typically bounding volume hierarchies, that allow you to trivially reject large portions of your scene when testing against array. So if you have 10 objects, you can compute 1 bounding box per object. You could imagine just intersecting with the bounding box first. If that doesn't intersect, then you know that it cannot intersect with any of the primitives inside that bounding box, so you can call them out immediately, right? That's the concept behind an acceleration structure. And acceleration structures are required for efficient operation. And because of this, we're adding acceleration structures to the API for ray tracing. And what we're exposing is a dual-level acceleration structure, where you have your bottom-level nodes that contain actual geometry, your triangles, and these are collected into a top-level node, where the top-level node has pointers to bottom-level nodes, and each pointer has some information associated with it for transform and shading. So, think of it like the bottom-level nodes contain your mesh data. The top-level acceleration structure contains instance information for your meshes. So if you have the same mesh repeated 10 times, you have 1 bottom-level node with 10 pointers with different transform and shading information. These are opaque data structures. They're completely implementation defined. IHVs are free to optimize and implement them as fits their hardware best. And we're speccing them out to have efficient build and update operations that happen on the GPU. And so the way to build these acceleration structures, there's a 2-step build process. So first, you're going to build your bottom-level acceleration structures, which contain the actual scene geometry. The intent is that you can actually reuse your existing vertex and index buffers that you're also using for your rasterization paths, and you can reuse them unmodified. You just feed them into this build and update operation. This happens on the GPU. It generates bottom level nodes for you. And once you have these bottom level nodes, you can take them, couple them with the transform and shading information, run a command that on the GPU generates the top level acceleration structure. Conceptually, pretty simple. So how do you create and manage these objects? Well, these are, acceleration structures are a new object type. They are created and managed in a very analogous fashion to other Vulkan objects. So you create an object, pass in some information about what the object characteristics are. That gives you a handle, and then you're expected to allocate memory for that handle separately. Just like for an image, you're going to create the image first and query it for how much memory do you need, allocate the memory and bind it. It's the same for acceleration structures. So there's a new object type with the create info struct associated with it, and also a new descriptor type for binding these top-level acceleration structures to shaders. You can't actually bind the bottom level directly as a resource to a shader, but you can bind the top-level acceleration structure. And for memory management, again, the backing store is managed directly by the application, just like you would for a texture. There's a get memory requirements call for acceleration structures that gives you a number of bytes to allocate per acceleration structure, and you're responsible for allocating those and binding them. Memory requirements will vary, and specifically, you'll note that we're actually giving the application a number of bytes before we've actually seen the geometry, but in many cases, that's an upper bound. And so there is a compaction operation that you can do once the build has happened. You can actually query the API for how much memory do you actually need for this piece of geometry, and it'll give you a number that's likely lower than the initial upper bound. So there's a copy command that allows you to copy acceleration structure objects while compacting them if desired. And this is mostly the intent of the copy command. Oh, I'm sorry. I skipped ahead a bit. This is the intent of the copy command. It's to allow you to do compaction on the acceleration structures once the implementation has actually seen the data. Now, I'll just briefly mention the build command that I described earlier. This is a standard command that goes on a command buffer. There's a single command to build and update. There's a flag that you set to determine whether it's a build from scratch or an update. We're defining updates separately from initial builds for reasons of efficiency. If you're doing an update, typically you're just moving vertices around. You're not changing the number of vertices, so that's one of the restrictions. The number of vertices in an update must be identical to what the bottom level node was initially created with. Updates are separate because you can typically do updates much faster than a build from scratch. So if you're animating characters in your scene and whatnot, you want to do updates and not build from scratch every frame. So we've covered the copies. Let's talk quickly about the new ray tracing shader domains that we're going to define. So quickly, we're going to talk about 5 new shader domains. So that's RayGen, ray generation, any hit, closest hit, intersection, and miss shaders. And we're also going to define new primitives for these shaders to communicate amongst themselves. So let's start with the inter-shader communication. We're defining what we're calling a ray payload. And you can think of a ray payload as essentially a piece of data that's attached to the ray that the ray is accumulating as it traverses the scene. It could just be a color, right? Or it could be, visibility information for shadow rays, or it could be, a spectral density if you're doing light transport simulations. It could be anything. It's entirely application defined. But the idea here is that you initialize it in the ray generation shader, and all the hit shaders can update it. And then it gets the data, after it's updated, gets returned back to the original ray generation shader or to the shader that spawned the ray to begin with. So this is used to return final intersection information back to the original shader stage that spawned the ray. We're also defining what we're calling ray attributes. These are essentially intersection information passed between a custom intersection shader and a hit shader, right? So I mentioned you can define a custom intersection shader. It's going to intersect arbitrary kinds of primitives. You might want to do one for nerves or something like that if you have such things in your scene. And whatever data you need to emit from the intersection shader is up to you. So you can define in your application what kind of data structure you want for data to be passed between the intersection shader and the hit shaders. So onto the new shader domains themselves, starting with ray generation. This is essentially, think of it as a compute kernel. It's kind of what it is. It's a 2D grid of threads launched from the CPU. It's a starting point for all ray tracing work. I think crucially, the main difference between this and the compute shader is that there is no access to shared memory in a ray generation shader, but otherwise it kind of behaves similar to a compute shader. So you get your grid of threads, you get your index for each thread in the grid, and so on. Based on that, you compute which rays you want to shoot for each thread, and you call a built-in primitive to trace those rays into the scene. It's also responsible for writing the final output, right? So reminder that we're not going through rasterization, so there's no implicit ROP to output your data through. So your RayGen shader has to explicitly write data out to memory. So I mentioned the custom intersection shaders. These are meant to compute intersections with application-defined primitives. Ray triangle intersections are built in, and they're typically much more efficient than what you might get with a custom ray triangle intersector. So if you're just intersecting triangles, don't use a custom intersection shader. IHVs will typically provide much better implementation based on hardware features than an application could write in high-level code. The same is true for axis-aligned bounding boxes. That's also a primitive that you can intersect against. There's also built-in support for that. So the any hit shader stage, it's invoked after any intersection is found. So a ray will traverse the scene in some direction. It could potentially hit many primitives along the path of the ray. So any hit will be invoked for each of these intersections. And there's no defined order in which these invocations will happen. They could happen in parallel. So there's no constraints on how the implementation will call your any hit shader. But it will be called for every intersection that is found along the path of the ray. Then we have closest hit shaders, which are called just for the closest intersection along the path of the ray. Both of these shader stages can read attributes and trace rays to modify the payload. Right? So you can spawn rays from any of the hit stages, and you get access to the ray payload as well. And finally, we have the miss shader. So if there's no intersection found in the scene, or if your shaders reject all of the intersections, which you can also do, then the implementation will determine that there's no intersection to be found. So it will invoke a miss shader. This is where you can do stuff like, draw your sky model or something like that, because your ray went past the scene and didn't hit anything. Similarly, miss shaders can trace rays and modify the payload as well. So how does this actually look in GLSL? So the ray payload and intersection attributes, they're new block decorations. So you declare global variables with these block decorations, and that's how you specify what your payload and intersection attributes look like, right? And so when you call trace, you're going to pass in a reference to a payload variable to be read and written by subsequent shader stages. There's a bit of a nuance here that I want to try to explain, in that this really implies that trace NV would be polymorphic, but GLSL has no concept of type polymorphism. So instead, to overcome this limitation, what we did was assign a location index, or allow the application to assign location indices to each of the payloads that it defines. And instead of passing in the payload by reference, directly by saying, okay, trace NV against first interface, trace NV against second interface, what we do is we use the location index as the reference, right? So trace NV will receive an integer argument that corresponds to the location that was defined for each of the ray payloads. This has to be a compile time constant, and the compiler will generate type polymorphic code underneath, but this was the mechanism we found to avoid having to specify full type polymorphism for GLSL. And so I alluded to trace NV. That's the built-in that will trace a ray from a shader. You pass in the acceleration structure as an argument, and you can have multiple acceleration structures bound to your shader. They're just regular Vulkan resources at that point. There is a bunch of other arguments, some of which have to do with the indexing scheme into the SBT. I'll cover that briefly in a few slides. And you also pass in your Ray information, right? So trace NV traces a ray into the scene. That's a new built-in function. There's also report intersection to output intersection information from an intersection shader. And you have ignore intersection to reject a given intersection that was found. And you have terminate ray to stop processing the current ray. There's also some new built-in variables and new declarations to give you access to various pieces of data from like your thread ID and RayGen and so on. So I've mentioned the shader binding table a few times. Let's look at what this is. So unlike rasterization, where you have a mesh and you might have a PSO associated with that mesh, and you might have a bunch of descriptors also associated with that mesh that bind specific resources to the shaders. Well, with ray tracing, you can hit any mesh, and it can have any kind of different shader that you've specified before when building your assets, and it can have any kind of like different textures, different buffers. It may need different resources available. And because you can hit any of the meshes in your scene, this effectively implies that you have to have all of your scene resources available to the ray tracing PSO or to the ray tracing infrastructure all at once, right? This is where the shader binding table comes in. So the shader binding table, think of it as a buffer with a number of records, where each record contains a shader handle that identifies one shader, typically a hit shader, but could also identify a RayGen shader, and it has a bit of data associated with it, which is application specified. So these records have an app specified stride, and they exist inside a regular Vulkan buffer. There's an indexing scheme to figure out which record to pick for each ray tracing operation that is happening. And because the application defines the stride, this can accommodate any kind of data that the application needs to associate with each shader or with each geometry instance, with each mesh, etc. And this is kind of a quick schematic of how it works. I'm not going to go into a lot of detail. The indexing scheme is a little tricky, a little complex, but you get the hang of it pretty quickly. I would recommend looking at the spec for details, but essentially you can see that there's a number of records with a fixed stride. Each record has a shader handle at the top, and then it has custom data, custom indices. It's just data that shows up as a buffer on the shader side. The intent is that you'll stash indices into these records that will then be used to index global descriptor arrays using descriptor indexing. So that's how you get access to your resources. If you know you need a given texture for this particular geometry, then you're going to put the index of that texture in a global array in the SBT record, and you're going to make sure that this texture is actually bound in the global array to get access to it. And so some of the indexing information comes through from CMD trace rays. That's the base RayGen index. Gives you the index into the SBT for the RayGen shader. So invoke CMD trace rays. The API will take the index that you pass in as the RayGen index, will index into the SBT, pull out their shader reference, and execute that shader as a RayGen. And then when you call trace within the shader, there's similar indexing arguments that will tell the infrastructure where to start looking for the next shader in the ray tracing chain. And there's further elements to the indexing that allow you to offset based on which geometry you're in, which primitive or which mesh you're processing, and so on. So it's flexible enough that you can express pretty much any combination of different records that feed into different meshes and different instances and so on. Right, so onto the pipeline itself. The ray tracing pipeline, it's actually relatively simple compared to the raster pipeline. It basically is just a collection of shaders. It's all of the shaders that you need to get into your scene in order to trace against it. You can have multiple shaders in the same stage. That's unlike raster PSOs. It's really literally just a collection of shaders. There could be many, many shaders in a single ray tracing PSO. So there are facilities provided to allow you to multi-thread your compiles across shaders within the same PSO. So typically with raster, you create a pipeline and the compiler will compile all the shaders in that pipeline in the same thread where you called create pipeline. For ray tracing, you can defer that to different threads. There will be primitives available to enable you to parallelize compiles within the same PSO, again, because you could have hundreds of shaders being compiled. And the shader handles that we put in the SBT are exposed to the application as opaque handles that you query from an API call on the CPU side. So the flow is compile the PSO, then query the shader handles, and then write those handles back into the SBT in the appropriate locations. And finally, we have the trace race call. So this is what triggers ray tracing work. Regular command buffer commands can be invoked in both graphics and compute, and it reuses the existing bind pipeline functionality. So there's a new bind point for ray tracing PSOs, which you can use for both bind pipeline and bind descriptor sets, and TraceRays makes use of that. So for more concrete detail, here's a sample, relatively trivial ray generation shader in GLSL. So up top, we have the acceleration structure. That's a resource. There's a descriptor set type associated with it. You bind it as you would any other resource in Vulkan. And we also have a frame buffer image. That's just a plain to the read-write image that you're going to emit your data into. We have a uniform block that gets a bunch of parameters. They are related to the SBT indexing, where you may want to have different chunks of the SBT per execution of this shader. So we pass those in as a uniform block. And then we define the payload for the rays that we're going to shoot. And this payload just has a color value in it, a vec4 color value. So then in our main function, we start by initializing the payload, so it has a well-defined state. Then we call trace NV. We pass in all of the parameters related to the indexing scheme. We pass in the scene parameter, which is an acceleration structure. Again, we can have multiple acceleration structures, which we can use to combine, different multi-pass ray tracing algorithms into one shader. In this case, we just have one, so we pass that in, along with the ray information, where we compute a direction for the ray based on both the input uniform block data for the origin and direction, with some jitter based on the thread ID, which maps to a pixel on the screen in this case. So we call trace. That's going to update the payload. It's going to run the ray tracing infrastructure, generate a ray, trace it, run the hit shaders, and it will update the payload. And in this case, all we do is just write out the color information that we get from the payload out to memory through the frame buffer image. And this is the closest hit shader that goes with that RayGen shader. All it does is take the world space position of the intersection and sample a 3D texture based on that position. Relatively trivial. This is a sort of a toy example, but just to show you how the whole thing comes together. So we declare the payload identical to what the RayGen shader declared. This has to be the same struct. In this case, each hit shader can only have one payload type, so there's no location information associated with this. And we have a 3D texture that's bound just like a regular Vulkan resource. And then our main function for the hit shader, we use some of the built-ins to get intersection information, compute a position that we're going to sample the texture from, sample the texture, and write that result out to the payload. Fairly simple. A less simple example, and this is more or less GLSL pseudocode. We actually took this from a real working ray tracer. This is the main loop for an iterative path tracer written in GLSL on a RayGen shader. So if you've done a relatively modern path tracer with next event estimation, Russian roulette for termination, all of that stuff, even on the CPU, you may have seen a loop that's very similar to this, right? And this is to show that you can do pretty much the exact same thing with ray tracing on Vulkan. So you can implement a ray tracer that looks pretty familiar and runs pretty efficiently on the GPU. This is, in fact, while we support recursion, NVidia does not actually recommend recursion for ray tracing in general. And the same goes on a CPU. Typically you want to avoid recursion, so you end up with a loop like this, and it maps pretty well to the ray tracing API. That's basically the point that we're making here. So I talked a lot about GLSL, but I know that in the games industry in particular, HLSL is a lot more popular. There is support for, in the DirectX shader compiler, Google has built a backend that generates per V in DXC, and this is part of mainline DXC in the Microsoft repo. And NVidia recently contributed support for generating SPIR-V from DXR shaders that targets the NVidia ray tracing extension. This is also in mainline. If you go to the Microsoft repo, pull it out, build it, it's there. You can compile the XR shaders for Vulkan using the NVIDIA vendor extension. We expect this to be easy to convert to the cross-vendor extension later on, and we intend to contribute support for the cross-vendor extension to DXC as well. Now, one caveat is that the resource binding model for ray tracing is different, significantly different between DXR and Vulkan. So in DXR, the shader, the records in the SBT, there's an SBT just the same, but the records contain what DirectX calls a local root signature, which is essentially a map of resources that are available to that to the stage that is executing on that SBT record. Right? So if you have a hit shader, you can put in buffer references in your SBT and the local root signature directly, but you can't do that with Vulkan because the SBT is just data, and Vulkan does not allow you to have a pointer to a texture or a pointer to a buffer as data. With the caveat that device buffer address actually allows buffer pointers, limited buffer pointers, to be expressed in memory. So you can actually put those in the SBT, but you can't have a handle to a texture in the SBT in Vulkan. So the intent in Vulkan is that instead of having a local root signature, you use global descriptor indexing, and the SBT records will have indices into these global arrays. We did do, at NVIDIA, we did do some design work to try to emulate local root signatures on top of our vendor extension. And the conclusion was it's doable, but we haven't actually done implementation work. This is because we've gotten feedback from various ISVs that are trying out ray tracing and implementing ray tracing in their applications, especially for applications coming from DXR to Vulkan. The feedback we got so far is that this isn't actually required in practice. Most applications seem to use the local root signature to just store constant data, and they seem to do indexing into global arrays anyway, despite the fact that DXR allows you to stash resources directly in the SBT. So in practice, what we've done so far for HLSL support is expose the SBT as a constant buffer. So in your hit shaders, the SBT record will show up as a constant buffer-like binding. And this seems to be enough to, in practice, solve the problem of resource binding for ray tracing shaders. So this is the approach we're going with. If there's enough feedback, if there's enough of a need for something more complicated or more useful in terms of emulating the local root signature, we can certainly consider that, but we think that this is, based on developer experience, this seems to be the way to go anyway. And so that's it. Ray tracing is coming to Vulkan. Kronos is hard at work coming up with a standard. This is driven by industry interest, and there's a growing ecosystem of applications that are targeting Vulkan and also ray tracing, which this will enable to run in a cross-vendor fashion. The current design that's being worked on is largely compatible with the shipping NVIDIA extension, so we think that it's a good target for prototyping, even if you plan to ship only on a cross-vendor extension. Again, same caveat applies that it hasn't shipped yet, so things could change. I think there's a fairly low likelihood of it turning out to be incompatible, but that is the caveat that we're putting out there. And that's it. Any questions?